Okay, let's dive right in. We're about to go on a quest to solve one of the biggest mysteries out there, and it's a mystery that's happening inside every single one of us right now. We're talking about the mind. And I don't just mean the brain as a piece of hardware, but the very nature of our conscious experience itself.
I mean, really think about that for a second. Everything you've ever seen or felt or thought about, the sound of your favorite song, the feeling of sunshine on your skin, that memory of your first big success, all of it, every last bit, is generated by this thing, this soft 3-pound lump of cells. How is that even possible? It's a question that gets to the very heart of what it means to be human.
And this quote from the philosopher David Chalmers just nails it. He calls it the explanatory gap. See, we can get really good at describing what the brain does, which neurons are firing, what chemicals are being released, but we can't seem to explain why all that physical stuff should feel like anything at all from the inside. And that gap? Well, that's the mystery we're exploring.
So where do we even begin? Our quest starts with the cartographers of the mind, the neuroscientists. Because if we have any hope of understanding the mind, we first have to understand the incredible machine it runs on. We need to map out the brain's fundamental mechanics.
You know, at its core, the brain speaks one language, and that language is electricity. The fundamental unit of information is this thing called an action potential. It's basically a tiny spark, this little flip in electrical charge that zips down a neuron faster than a race car. A single neuron can do this hundreds of times every second. This is the code, the ones and zeros, that underlies every single thought you have.
And here's where it gets truly amazing. One spark is simple, right? But billions of them firing together in these incredibly complex networks, that's a whole different ballgame. These networks don't just react to the world around you, they actively build a model of it. They create a kind of simulation of reality right inside your head. But how can we be sure that's what's happening?
Well, let's look at a fantastic example called place cells. Scientists found these neurons inside the brains of rats, and what they saw was wild. One specific cell would fire only when the rat was in one particular spot in its maze. Another cell would fire when it moved to a different spot. And together, these cells create a living firing map of the environment inside the animal's brain. It's the perfect demonstration of how physical brain activity builds an abstract mental picture of the world. But here's the question. Does the rat feel like it's in that corner, or is it just a biological GPS executing a command?
So if we start to see the brain as this biological computer, building these complex models from simple little signals, it leads to a pretty tantalizing question. Could we build one ourselves? And this brings us to the engineers on our quest, the pioneers of artificial intelligence. For a long time now, AI research has kind of gone down two main paths. On one side, you have disembodied AI. Think of a program called NetTalk. It learned how to read text out loud just by analyzing huge amounts of data on letter patterns. On the other side, you have embodied robotics, like this robot from MIT named Cog. Cog was designed to learn by actually interacting with the world, touching things, moving its eyes, basically like a human baby. So one learns abstract rules, and the other learns by doing.
The way these systems learn can feel like actual magic. Take NetTalk again. It started out just babbling, making random sounds for letters. Total guesswork. But after being fed thousands and thousands of examples and correcting its mistakes over and over, something incredible happened. It didn't just memorize words. It suddenly started to understand rules it was never explicitly taught. It figured out the concept of a vowel, all by itself. Just by finding the pattern, it went from memorizing to actually understanding.
Okay, so we've mapped some of the brain's signals, and we're engineering machines that can actually learn. We're getting really, really good at explaining how the brain processes information. But, and this is a huge but, all of this incredible work brings us right back to our central mystery, the ghost in the machine. What is all this mechanical complexity still missing?
It's missing this: phenomenal consciousness. This isn't about what the brain does, it's about what it feels like from the inside. It's the raw quality of an experience. A computer can process the exact wavelength of the color red, sure, but does it have the actual subjective experience of seeing redness? That is the question.
And that, right there, is the hard problem in a nutshell. We can explain the so-called easy problems, how the brain takes in information, how it controls our behavior. But why isn't all of that processing just done in the dark, without any inner feeling at all? Why do we have this rich inner movie playing in our heads? So far, science doesn't have an answer. This leads us to this really wild thought experiment, the idea of a philosophical zombie. Now, imagine a perfect replica of you. It talks like you, it laughs at your jokes, it even says ouch when it gets hurt. From the outside, you absolutely cannot tell it apart from the real you. But on the inside, there's nothing. No experience, no awareness, no consciousness. Just an empty machine running a very convincing program. Could a thing like that even exist?
You know, this isn't some new problem we just invented. This feeling of a deep mystery sitting at the very center of our own minds is something people have been grappling with for centuries. All of our modern science and engineering, it's really just the latest chapter in this epic, ongoing story of trying to figure ourselves out.
I mean, go back over 300 years ago, and you've got the philosopher John Locke wondering if God could somehow make a rock think. Then fast forward to 1950, and Alan Turing is challenging us to figure out if a machine can be intelligent. Then you have the work on Cog in the 90s, trying to build a mind from the ground up. And finally, in 1996, Chalmers gives our modern puzzle its famous name. It's been a long and profound journey.
This quest is just so massive, it needs everyone on board. It's like a grand expedition. You have the neuroscientists, they're the cartographers, meticulously drawing the map of the brain. You've got the AI researchers, they're the engineers, trying to build a brand new kind of vessel. And then you have the philosophers, they're the navigators, constantly asking the really important questions. Where exactly are we headed? And why does it even matter if we get there?
Which brings us to a final, really important thought from the philosopher Daniel Dennett. As we get better and better at mapping our brains and building new minds, we gain this incredible power to know ourselves. But, as he warns, that opportunity to know can start to feel like an obligation to know. So as we push forward on this quest to unlock the secrets of our own consciousness, the question we're left with is not just what we're going to discover, but what this whole journey of discovery is turning us into.